but we have not been able to do it. We have given it to many batches. The problem is, of course, mathematical and trivially stated. I will take, this is the beginning of the chess game. This is some random arrangement of pieces which I will give you. Don't worry about checkmate or win or loss. Just by making black and white moves alternately, either you generate this or prove that it cannot be generated. Obviously there are some trivial things out here. If I give two bishops of the same color, it cannot be done. Similarly, if I give you three bishops and there is no pawn promotion, it cannot be done. So the trivial things you can leave. Now what is remaining is one king, one rook, one queen, one pawn and one horse for white, and one king. Okay, there has to be a king, so we put a king, one queen, one rook, two rooks and four pawns for black. Now they are arranged in this. This may be a horrible position for a chess master. One of them, one of the sides may have lost. Now, I am not interested in that. I just want to know whether you can generate this or not. Now, from computer science point of view, this is also a trivial job. Only it is a graph reachability problem. The initial node is specified. Every node reachable from it is by a generator, by the chess move. That is also specified. And this is a node. The only problem is, it is actually order 1. In that the size is a constant. It is not even order n, it is only 8 by 8. Only the constants there are 10 to the power 43 to 10 to the power 45. And that is as far as we have got in this. We have tried very hard to use many techniques, but we know of no method which can unambiguously or even probabilistically answer whether a certain configuration of a chessboard is reachable from the initial position or not. So what we will do is, this will be a tiny little prize for this conference. If somebody can solve it by tomorrow, we will give them some grand prize. If somebody can solve it in a month, we will give them a slightly smaller prize. If it's not solved till next year, it rolls over. So this, we have tried to do this. We have tried to use problem methods in robotics and so on, where they use configuration spaces. They try to probabilistically find out configurations which are reachable from an initial one. But we have not practiced. So it's, I think, it's a most discrete, it's a very discrete problem, very well known problem. Only it's a slight twist on the same game. So I don't know if there are any advanced mathematical techniques which can help us to deal with problems like this.
Transformation, trace back.
No, not even trace back. Don't worry about inverse. That's a different problem. I am simply saying this is the initial state. This is the state to which you have to get it. Or use chess moves and come up with the sequence of moves, or prove that none exists. I mean, the trivial things are, if there's two bishops of the same color, obviously not possible. Those trivial things you rule out. Then the other is a general one. I'm not even sure whether you should pose this as a graph problem or maybe more like a language acceptance problem. This is a string in a language, and this is the set of transformation rules. Can you accept this? Does this belong to the language or not? That may be another way of looking at this. But in general, I do not know of any method, any general method for this. So, I don't know. I don't know if the mathematicians are interested to tackle problems like this.
No.
Only one question is that whether these positions, you thought of this position or just like that you kept it?
Right now, we just kept it like this. We have not.
You told that you tried this one, but the same position you tried or different?
No, some other. No. I did not try.
That's what I want.
I don't know. I don't know the answer to the question.
So assuming that even the other fellow may not be opposing, suppose it can kill,
It can be
not kill
cooperative.
it.
It can be cooperative.
Ah.
You can make it competitive, which is even more complicated.
Yeah.
Let it be cooperative. That
Cooperative,
both white and black will cooperate. We have
To
to
reach
get
this stage, to reach this
to
stage.
reach this stage.
Yeah.
Can you what can you do? We have not found any answer to this question.
When thought occurs, going back to Gödel's thing, because you said about language, you can say this is a statement. One wants to know that this is a grammatically correct statement.
Yeah, okay,
Meaning
okay.
grammatically correct, meaning proper chess moves.
Yes, yes.
Yeah, but then the impossibility theorem, I mean, Gödel's this thing says there could be statements which can neither be proved right nor proved.
But
there may
No,
be-
this is not like that.
This is not like that,
This is
because this is-
finite thing, no finite.
It's finite, completely finite, and you can enumerate it. You can enumerate it, but
All is huge.
the enumeration is impractical, completely impractical. So enumeration is okay. There is an existence proof, but the existence proof is of no practical utility. I mean, you can create a graph if you have that many atoms in the universe or something like this and that many cycles. You can create the graph.
One thing that you try to trace back.
That's what, that is the.
But he is an expert, no? So he is what he knowing.
No, I don't know. We have not solved. This is a problem which we have not been able to solve. It is typically not posed in the chess literature much, but it is a perfectly legitimate problem to ask of the chessboard. Based on and then some extensions of this, we actually play chess backwards in time, where we try to reconstruct the initial state from the final state. We'll show you that game. You can play the game. You can, from legitimate chess positions, you can create positions which can never occur in chess. I mean, what can happen is you can put 3 pawns like this, which cannot occur because this pawn could never get there. But you can create it when you go backward. So it is, I think, the set of connected components. Okay, the more general version of this is characterize all the connected components or equivalent classes of the chess graph. That basically probably the most abstract specifications of this problem. So basically, can you count the number of connected components in the chess graph?
No, but all are linked to the first move, no?
Yeah, you can look at
So
this.
that point is connected to all paths.
Yeah, this part, no, it doesn't have to be. You can make the problem
I
as
see.
mathematically
Okay.
general as possible.
Okay.
One question is what
Starting
are
from in between stage to another stage.
yes, ultimately we want to say we know just like I believe all groups have been enumerated and so on and so forth. Have you enumerated all?
Oh, yeah. If this cannot be obtained from the initial stage, so this belongs to another equivalence class.
Yes, exactly.
Okay.
So this, given that Vishwanathan Anand has given us unbelievable motivation in this game, so this is something which I think is a very, very simple problem. It's sufficiently simple that engineers can understand it, and we have not been able to solve it.
No, the thing is that number of white and number of black, they are different. So what is the motivation of to keep some randomly that one?
No, it is basic. It's a mathematical problem. Okay, if you want to keep equal, even that we have not been able to solve. Let us say you want to keep equal, even that we
He's
have
not particular about that kind of configuration.
Yeah, usually they get killed.
Just an arbitrary
Yeah.
fixation.
So, I don't know. I think maybe ultimately the way to handle something like this will be an in-depth study of the maybe group theoretic structure of the chess moves. What can you classify
Is it
them?
useful somewhere? Is it? Let me ask you.
Where?
Because we spend-
Which idea?
Mathematician asking about useful things.
No. This is no, even mathematically
Well, it's entertaining for us, and we have not been able to tackle this. So now, to get more useful, Abhilasha has come. So let her talk, and afterwards I'll have a few things.
Yeah.
Good afternoon, everybody. My name is Abhilasha, and I'm a PhD student. Okay. I'm a PhD student with the Computational Sciences Lab here at IIIT, and Prasanna sir is my advisor. So I'm just going to talk about a few mathematical topics which are of interest to us. So basically, we all work in optimization, and optimization is the domain of applied mathematics. We have nothing to do with pure mathematics, but still there are several topics of interest and many connections that connect the two fields. So a general optimization problem is minimizing a function f0 of x subject to a set of functions. So in general, this is a non-convex optimization problem which is extremely hard to solve, and exact solution procedures, they enumerate all the feasible points and pick out the minimum, the point which gives the minimum value of the objective function. And they are not computationally very attractive because the procedures are mostly NP hard. So an interesting class of problems is when the objective function and the constraints all are polynomials. So this class of problems is known as polynomial minimization problem, and there are many examples of polynomial minimization such as testing, matrix copositivity, sequence partitioning, max cut problem, etc. The general problem is of course NP hard, but there are some approximation techniques which rely on semi-definite programming, which interestingly are polynomial time and give us solutions which are reasonably close to the optimal that we are looking for. And the interesting part is that the problem reduces to finding a real number lambda such that fx minus lambda is a sum of squares. And this problem can be solved using semi-definite programming in polynomial time. The only thing is that this real number lambda that we get is the lower bound to the optimal answer that we are looking for. And in most cases, this lambda is actually equal to the optimal point in most practical cases. So these problems are of great interest to the optimization community, and very interestingly, they use concepts from algebraic geometry to derive these relaxations. So,
is it a lower bound or an upper bound?
Lower bound. Because semi-definite programming, they use duality. So duality would be maximizing some function, and that maximum will be smaller than this. So algebraic geometry it originated with Hilbert's 17th problem, which asks whether every positive polynomial can be represented as a sum of squares, and the answer to that is yes, which was given by Emil Artin in 1927. And it tells us that for every positive polynomial there exists a representation of that which is a sum of squares. And then there's Hilbert's null stem. So that's the famous theorem of zeros, which tells us that every polynomial system of equations you can either it is feasible, or you can generate a certificate of infeasibility for it. So this is for fields which are algebraically closed, and like the complex field of complex numbers, and it does not give us any solutions for the real case. So there are several positive Stellenschadt's theorems which deal with the real case, and what they tell us is that given a system of polynomial equations, either it is feasible, or we can generate a certificate of infeasibility, which is an identity. If the function, if the system is f then gx times fx is equal to hx, where g and h are sum of squares. So the positive Stellenschadt's certificates combined with the semi-definite programming techniques, they give us relaxation techniques for solving polynomial minimization problems. So this is the connection between optimization and algebraic geometry. And yeah, of course they gave us the lower bound lambda. Now there are several interesting questions based on this. We can use positive Stellenschadt's theorems to solve the equations of polynomial minimization, but can we use them to solve integer linear programming problems or integer programming problems in general? Can we use them to generate valid inequalities? And can we use the sparsity and symmetry in polynomials to exploit? Can we exploit sparsity and symmetry to generate more efficient algorithms? And how often is lambda equal to f star? We are saying lambda is a lower bound, but we don't know.
What is the scarcity?
Sparsity. There's a typo. It's sparsity. And if a special class of polynomial minimization is when we are minimizing a polynomial over a set of polytopes. Polytopes are sets of linear equations. So what is the quality of the lower bound if the constraints are all linear? And then the feasibility set of an SDP is a semi-algebraic set. Can we use real algebraic geometry to characterize it better? That's still an open problem.
Do you have any algebraic geometry results for any specific example? Any specific optimization problem?
Yeah, there are several references. These references are they apply these algebraic geometry methods to solve optimization problems, and they have many results. So mostly Pablo Carrello, he is at
I just
MIT.
wanted to see some examples so that we can go more and study things.
It will take
correct.
longer. So this is just to show that pure mathematics can be of great interest to applied engineers like us. And these are some problems. To solve these, we don't know all the mathematics, and you all can help us if we want to tackle these problems.
Yeah, we can give you some from network theory. There are specific examples where he has shown, there's a paper I can give you where he has shown these relaxation, these sequence of STP relaxations, and he has talked about exactly this stuff. Now one of the things is most engineers have no clue of these methods. Algebraic geometry is not a subject for almost any of the engineering disciplines. However, increasingly we are asked to deal with these kinds of systems. You can go ahead.
Then we have the topic of numerical precision. Ganesh is working on this and he'll elaborate further.
Yeah, our group is already working in numerical precision with respect to financial transactions. Because when we represent a number, a float in a computer, it is represented using IEEE 754 standard. And so how it is, the data structure, it has 64 bits, which is limited, but the real number should be represented with the arbitrary precision, but here we are concising, saying that we can represent only with 64 bits. So there is some precision error associated with every number we are handling. Also, what is happening is there is some there are some rounding rules applicable over that approximated value, and over that the currency handlers, they also do some rounding methods. So what is happening is the value we are handling is only the approximate one. So here there is a problem that we are currently trying to tackle. That is in a financial currency conversion network. It's an arbitrage network. What I'm doing is I have some money, I convert to some other currency, or I have to some other currency and come back, I'll get some extra money. So I want to optimize, that means I want to maximize my profit. So here what is happening is, because of this, the approximation, actually what I'm doing is I'm trying to multiply the values. Here it loses the associativity, because it is losing the associativity. What is happening is, suppose when I have A, B, C, A into B into C, or A into B into C. So there are a lot of ways by which we can do the bracketing. That is, there are approximately 2n choose n number of ways in which we can do, that is Catalan, order of Catalan numbers. So it's a very big problem in our hand to tackle. Apart from finding the shortest path, we have to currently tackle this problem, because the associativity law is lost because of this approximation. So this is what currently we are.
So how do you work with that?
Sir, currently we don't have to, because up to 2 power 45, the product is less than 2 power 45, it's actually a ring. So associativity is satisfied. When the product crossed 2 power 45, the associativity lost, and we don't have to. Actually, when you take real numbers, they are supposed to be a ring. So we are supposed not to face the associativity problem. But because of this approximation, which is associated with this floating point representation, we are facing this problem.
So what is the way of?
This is the current problem we are facing. We have to, because there are some dynamic programming techniques, like they use for matrix chain multiplication, where they have two properties, that it will not satisfy commutativity, but it will satisfy associativity. Whereas in our case, it satisfies commutativity but not associativity. So we cannot handle that algorithm. So we have to design a new algorithm for
So
it.
any finite precision will have these associativity problems.
Yes, sir.
Yeah. So
Yes, sir.
How do you work?
Sir, it's
So the idea is to find a bracketing which minimizes the
yes, sir.
damage.
Increase the.
Even Hamming is arguing like, yeah, this is the numerical precision is very important, but the field is not well developed like other fields in numerical methods. So it's also not well developed. Anushka will.
But I mean, what are the parameters you're dealing with here? Because the precision is, and there are a lot of dependencies, right? It depends on where the computation is happening, which machine, what software, what platform, what hardware. I mean, there are all kinds of. So, what parameters are you dealing with for doing this minimization?
Yes, sir.
It's still not clear.
Sir, currently we are assuming it's a floating point representation. IEEE 754 standard. There are ways in which we can completely avoid that.
So, are we sure that any two pieces of hardware which are compliant with the IEEE standard will give you exactly the same numbers?
So, if the product is less than 2445, it will give an acceptable result, sir. So, what will happen is, suppose if I want to handle up to 3 decimal values. So, if the output, the error is less than 10 power minus 3 by 2, it is acceptable, sir. That is called half of ULP, unit in last place. So, here, if the value or if the error associated is less than half of 2 power minus 53, it is acceptable. And this is ensured when the value or in the product is less than 2 power 45, because it has sufficient number of bits to handle or to represent that half of the ULP. When the value becomes large, what is happening is, suppose if this is the data structure, some of which is used to represent the actual number and some for the decimal value.
Right.
So if the value becomes larger, the number of bits for the decimal gets squeezed, so we are not getting that accurate result. So that is the problem. So up to 2 power 45 we are not facing that problem. After that we face this problem. But what we can do is we can go for arbitrary precision arithmetic or multi-precision numbers where this is completely avoided. But it is taking hundreds to thousands of extra hours. For every operation it is taking hundreds of extra cycles. It's very costly. On an average it's very, very costly. What we are doing is we are trying to give an intermediate data structure. Suppose if the decimal value is getting squeezed, what we are doing is we are trying to give some extra data structure. It's like a lookup table. So that instead of using the multi-precision library, we can use that extra data structure with the extra few clock cycles rather than extra hundreds of clock cycles.
So the problem really is not to find the optimal bracketing.
Sir, that is also included, sir. Optimal bracketing, because this bracketing is different from the bracketing for the matrix chain multiplication, because there it has different properties, like the commutative property is not
No, but if you're going to fix the precision issue, that's
yes,
what you described, then you will get back your associativity, right?
Yes, sir.
Then you have no issue.
Yes, sir, no issue.
So which is the problem you're solving? Are you trying to solve the are you trying to fix the precision problem, or are you going to take lack of precision for granted but try to
Both, sir.
find an optimal bracketing?
Yes, sir. So one thing is, if we solve one problem, for example, if I solve the problem of giving precision to everyone, the problem is universally solved. Another way is, let the problem be there, let this also be there. So how I can use this so that I will get extra money out of every arbitrary cycle I do.
Okay.
So what I do is I will cleverly bracket so that my profit will be maximized.
Right now we only have heuristic, we don't even have a theory about a shortest path and the calculations are not associated. I mean, you have exponential, you can enumerate things, but enumerative methods won't work. They are not practical. And in addition, these are non-linear because when you do, there's this rounding step involved in all these calculations. So the product, actually, if you cascade exchange rates, you simply cannot cascade two conversions. You cannot multiply the relevant exchange rates and get the exact answer, because there's intermediate non-linear operations involved. So the mathematical challenge is, with a limited amount of injected non-linear and non-associative operations, can you bound the error one problem would be to bound the error in these standard methods. Another problem would be to come up with something which is guaranteed to be closer of less error than the standard methods, and so on and so forth. Ultimately, it is graph theory where the metric is non-associative, and to at least mildly non-linear.
Okay, so this is a problem which is open for discussion. So let us say that we have a polyhedral set which is formed by the half-plane specification. So that means like I have a set of linear inequalities, and these linear inequalities are a set of assumptions that I am making. So the polyhedral region, the convex polyhedral region that is formed is actually a scenario that represents my uncertainty. And let us say that I have an ensemble, a large ensemble of multiple scenario sets like that. So what I need to find is, I need to find is there any commonality between the assumptions that I am making? Or are the assumptions that I have made, are they completely independent of each other? So these are some kind of problems that I am trying to solve. And these are important in like decision support systems. They are very commonly used there, where I want to know, is there something similar between the two assumptions or between two different scenarios? So in this case, what we have is like, let's say we have two convex polyhedral sets. What I'm doing is I'm seeing, is there an intersection between them? Is one a subset of the other, or are they completely disjoint? So these are some of the things that we're trying to solve. Now, in the case of continuous variables, do these operations, that is finding a subset, finding an intersection. So in the case of continuous variables also, they are heavyweight operations because we need to solve an LP. And when we come to the case of discrete variables, especially when the dimensionality is very high, they become like computationally intractable to solve. So what we want to know is like, instead of solving ILPs over there, what are the other fast algorithms that we can have to solve? Like maybe using the topology or the geometric nature of the structure of the problem.
Just like Woodson and Shards, can you come up with a quick certificate of the feasibility of a set of polyhedral, discrete polyhedral structures? You don't need to optimize over them, just tell us whether there is something or not. A related problem will be the counting the number of points or the volume of convex bodies. Interestingly, I saw a early paper by George Andrews himself on convex bodies, and he had actually derived some bounds. But here this is one of the first steps in, at least is the volume non-zero, is it a null set or is it a non-null set? The standard methods everybody knows is essentially such as try this, try that, put this condition, put that condition, and so on, essentially branching out. But you have a richer theory for this.
Yeah, but you learn to improve over those algorithms. You put the two polytopes together and form a set of inequality and a feasible solution.
Yeah, but the point is that whole process itself is very time consuming for now, and suppose you have to solve, I mean there are powerful methods, and they solve actually stunningly large problems, but they're still not fast enough to solve, let's say 1,000 problems thrown at us fast enough.
But how do you plan to approach?
And that's why we have some heuristics, but heuristics are not.
What kind of heuristics? Less.
No, it's like basically we take a LP relaxation of the problem, see if they are disjoint. Now say the LP relaxation is disjoint, okay, I can say the LP is disjoint. But if it is not, then something else.
What is the half-plane specification?
That is like with the inequalities. You have a two representation. One is the vertex representation and the half plane. So vertexes you specify them and the half plane is you specify the edges.
And you don't want to solve the ILP?
No, here it's, IIT solving is like.
I'll just sum up a little bit by pointing out a few more things out here. In the same mold, we are also, it is exactly the same thing. We encounter, I can shout, don't worry. Okay, so we have a standard, the optimization people have seen this left and right. These are supply chains, these are essentially flow problems, whereas material comes in and goes out, and what comes in has to go out. And at every node in the entity, you have a flow conservation linear equation, at least in linear systems, and you get essentially as a collection of flow conservation equations. Only the cross product of the number of nodes, the number of products, and the number of time steps means there's millions of equations in small chains also. So essentially you have a constraint system which is large number. Yes, and there are non-linearities in the systems. Yes, modularity, everything does not come in real quantities. There are integrality constraints and so on. Modern powerful solution methods can give us the solution in a wide variety of these systems, but we cannot at this. When you find the solutions, you can actually, all that the solution says, it gives you a list of numbers. It will give you a list of 1 million numbers. And now if anybody gives me 1 million numbers, I have no clue what it means. I have no clue to even find out whether the numbers are correct or wrong. I am not going to read them, and there is no way I can read more than 0.001% of what the output it has produced. So it's very easy to change one number and to completely miss it, since nobody on the average is going to go through the answers. What we want is, however, in this particular example, it turns out that the numbers fall into equivalence classes. There is essentially 3 equivalence classes. One equivalence class is 0, another is close to 0, and another is large. You don't have to worry about the numbers. And the whole system, the solution is described by basically just 3 entities. So instead of saying that x1111 is 0.001, I will say the first equivalence class composed of x ones from 0 to 2050, the second equivalence class is similarly composed, and so on and so forth. And then I can actually explain my system in a much more succinct manner. So now this, what I am talking about in various forms is called, has a large number of buzzwords associated with it. It is also called data mining, it's also called big data, it is called dimensionality reduction. You have a large amount of names for this. But to the best of our knowledge, there is as yet no systematic sophisticated theory for this. What we want is, essentially you have an integer linear programming problem or an integral polytope. And this integral polytope has to be somehow mapped to a this polytope has millions of dimensions and it has some funny structure. Is there an isomorphism to a much lower dimensional entity which is non-trivial in that it will preserve, let us say, relative volume. It will preserve relative extent relative to, let us say, some other large normalizing polytope. Does it preserve relative optimality, and so on and so forth? These are some of the questions which we have to answer. And I believe that you will require very sophisticated mathematical techniques to achieve these kinds of transformations. This is going to be absolutely central in the field, because I don't see any way that human beings and human brains can understand million number answers or even million dimensional systems. In fact, I would say the whole progress of, there are these, Professor Raghavan, who was just here a minute ago, said Lord Kelvin one, biological systems are, and I'll show you one, the most difficult. So he said biology is basically stamp collector. We have no laws which we can think about which are tractable for us. Similarly here, if I simply present a million numbers, essentially I have in no way understood the system. I need to have essentially something like, hey, you want to go back down, please? Are you okay? Okay, so what we can do is, we have to come up with some ways by which you can come up with simple models of the system. For example, people used to build temples and pyramids long before Newton said F equal to ma. But that one central result caused the whole field of science and engineering to flourish in many new ways. And yes, it was a low dimensional description of the world. There were only 3 variables and essentially time. So there was an equation, neat equation which Definici was able to crystallize. Can you come up with some such methods to find essentially structure where at the face of it structure does not exist? Now of course you will say you are asking me to solve the problem of making a human brain, but obviously we are not asking such a open-ended question. Are there concrete steps you can take in this domain from our knowledge of mathematics as it exists? This is one set of questions which we are interested in. And in the same style, you will come up with exactly, philosophically, this is exactly the same thing. This is from biology, but philosophy, it's exactly the similar type of thing. This happens to be a model of a cell. We don't have to go into any of the details. However, and let us try to blow this up, and again we don't have to see any of this beyond. You will find some large number of equations. So now, and if you want some further you want a little bit more details about this. This happens to be also taken, yes. Here there is some more complicated structure, and there are about 100 coupled nonlinear equations in 100 variables. Now anyone who reads this will say, if for example, if any of us give a homework assignment to a student and they say, okay, they present this as their answer, it's very unlikely we give them even 1 mark. We'll say you don't understand what you're doing, you simply copy down a set of things so complicated that I could not correct it. So, and you don't understand the first thing about what's going on here. You have presented absolutely no model about this. I want something where you say, okay, this particular structure comes out cleanly and this is the basic behavior of the system. Yesterday Vijay Chandru was here. He says, for a complete description of biology as we know, that is well past any mathematics which we are at least aware of. It may be well past the mathematics which has been developed to date itself. What we are able to do is, if you tell us a specific application of the model, we can come up with macroscopic models which approximate it. There will be large number of experimental measured numbers in there, but we will be able to, but it will be restricted to that application and that parameter. Like engineering systems, yes, in principle you can predict how a bridge will behave under normal load, and in principle you can behave under heavy wind load, and to a limited extent you can predict what happens when things break. Even that has not been solved. Everybody knows that turbulence is also a clay mathematics problem as of now, and the Navier-Stokes equation itself is not resolved mathematically. You people are far more aware of these things. So, but this is the same thing. Can you come up with maybe a 2 or 3 dimensional? I tell you I'm interested in certain parameters. Is there a theory which will tell me from a complicated set of mathematical equations specifying the dynamical system, what is its behavior? I want 2, 3, at most, I would say ideally 2 variables, ideally 1 variable, but 1 variable may not get you much. 2 or 3 variables is what I'm interested in. It could be non-linear, but this, or else say that it just cannot be represented like this. The point is, if you say there is no simple model, then I would make a very dangerous statement that a system as complicated as biology can never be understood in the way we have understood science so far. In fact, I once told, I was talking about this to a mathematician. He says, you may be right, but you will anger the scientific community so much, you will become very, very unpopular. But the simplest, this is the same type of It is essentially the same thing. The simplest protein or the simplest prion is 4000 atoms. Yes, you can write the Schrodinger wave equation if it is a parabolic PDE, and yes, only there's 4000 entities in the system. Two body problems we know how to solve. Three body, I think itself is non-analytic. There's this famous, I think Abel or somebody proved is long back. And 4000 atoms, we have no hope. So now the question is, if you cannot do it from these principles. So what mathematics can help us here? Maybe we'll have to go to deep things in algebraic geometry, if only for the fact that these systems are inherently nonlinear. There is some inherent nonlinearity, and the linear algebra we are taught will not enable us to handle global nonlinearities and global behavior. We can locally linearize systems, but we cannot look at global topologies and things of this kind. So anyway, I think this is still in the same flavor and the same style as the previous remarks. The problems are extremely complicated and have very many parameters. We want some mathematics to help us simplify. So, and I do believe, even without knowing one word of it, there is a huge amount of literature which we have never been exposed to for some of these things. Of course, what the first things in dynamical systems you would talk in this particular thing is, yes, you know, look at the topology, look at the attractors, look at the repulsive points, and you can categorize them, but that is at a very general level. There is much more. We want a much richer theory. We know, for example, b squared minus 4ac characterizes certain behavior of quadratic systems. Is there such a behavior of a general nonlinear system you can come up with? Anyway, so this said, I will actually, while I don't have any slides about the same thing, there have been methods to handle some dimensionality reduction. We will not go into all of that. The same ideas are applicable, and actually I would say one of the state-of-art research topics in algorithms itself. We had talked about the complicated optimizations and integer linear programs. Most of them, even the simplest ones among them, are NP hard. It is, and in the worst case, it is only exponential algorithms which will work. However, we find that by using an initial solution, making a change to it, iterating the change in just like a dynamical system goes, for large class of practical problems, it solves it, if not to optimality, to within bounds which are far superior to what the theory predicts. Again, this is the behavior of a complicated dynamical system, and we do not understand this. In fact, Richard Kahn himself has been saying we need to develop a theory of heuristics. Our theory is extremely weak. So I think there is a huge amount of interaction between pure mathematicians and applied mathematicians. There is mathematics which is there, which we have never been exposed to, and which will have very specific benefits in these fields. So with these few remarks, I think Professor Yogananda also wanted to have a couple of words in this topic, please.
Not exactly in this topic, but
And then what we can do, we'll have an interactive discussion about it.
no, so because it was interaction, as he said, and I am a mathematician who moved from a pure mathematics institute to an engineering college. So we have 4-year series is 4 terms and not any finite series. So there the problem was, mine is more related to more mundane representation of Indian languages on the computers, and then one of the revelations I found was, for example, the fonts for Indian languages. So maybe, I mean, it was a revelation to me when I learned it, and many people may not know. When you type a letter, when A and A appears on the computer, it is not like in a typewriter. It is not an image which is implanted onto the screen, but like a human being, it actually draws it. Meaning what is contained when you say a font is drawing instructions. You give points and then equations to solve write the curves. The problem with Indian fonts is that when the English language alphabets have been studied in great detail and they can. For example, here they may specify these 5 points and then it is just lines joining them. So it's actually a curve fitting problem. So what happens with the Indian languages, suppose you want to write Kannada R. So this, the only way currently is to give a huge number of points on this curve and then approximate. So if you want to blow it up and then still see it in a smooth way, you'll have to give more points, but that will make the file very big. So that's one reason why you don't have good representation of the fonts, and not many fonts. So this was what I was telling in my curve fitting class, and told the students that there's a very beautiful way of fitting smooth curves between points, the Bayesian curve. Very good. And one student actually implemented it nicely. So it's very difficult to, in other words, if I know the equation of this curve, then it's the font I can generate very easily. It's just one line. I just give that equation, and whenever the resolution is more, you just sample that many more times. So then you will get better and better looking up without blowing the size of the font itself. So we can't, so that was the thing, we can't of course get an equation which describes it completely, but you find as well. So doing it visually is the best thing. So what I suggested and what he did was that given any 2 points to fit Bayesian curves. So it's a visual aid, a Java applet. So we put points and then we minimize the number of control points, because that is what will know the size. And then once he got it on the applet, where you just see a line, I told him that maybe I will teach you Metafont so that you can actually implement, because Metafont also only uses straight line segments and Bayesian curves, cubic Bayesian curves. But then these kids are very bright. So I told him I will teach you tech and what is Metafont, and in 1 week later he came back and said he had done all that and he had ported from Java to Metafont. He writes this and then ports this entire thing as a Metafont. So you can generate. Then he faced a problem. He said it will not be just like this, but there is a thickness. So what do you do? So because I was familiar with some differential geometry, then I said it's parallel transport. Meaning if this is a curve, you have a curve and you parallelly transport it, and then you fill up. That is the thickness, so to speak. But then when you take curves like this, parallel transport is easy. But when you take curves like this, parallel transport also intersect. It's not exactly. But then the parallel transport was an interesting thing, so we wanted to implement that. And then we looked at parallel transport in differential geometry. So discrete geometry is now a very, very thoroughly studied topic. Everything in Riemann geometry is implemented as a discrete geometry thing. So there is an algorithm for parallel transport called the Schiltz algorithm. So he looked at that, and we were also able to improve the Schiltz algorithm a little bit more to fit the thing. So essentially when it's complete, what it will have is the following kind of thing. If you are in an aesthetic sense and can devise these things at a particular standard size, then you will be able to create a complete meta font of your own. So in some sense you can create a font of your own which you can use, which others can read. So that's the beauty of this thing. Hopefully it will be. And another area where I interacted with this was the optical character recognition, which unfortunately even after so many years we have not been able to do. But I am happy to say we did it for Kannada and we have also extended it for Tamil. I have examples to show. And for me there, the problem was most of the engineers unfortunately were taking the existing English optical character recognition and then trying to make it suit our language, which was very difficult. So for mathematicians I will take, it's a very simple thing. You have an image, let's say, and you have text on it. Sentences, then which each sentence containing words and each word telling the syllables. So the first level of the optical character recognition is to segment. First segment sentences you cut them, and then words, and then go into syllable, and finally each symbol you have will be represented, and it will be represented by a matrix. So the idea is, okay, I have a page which is scanned, and I segment it, and then I went to obtain a lot of matrices which represent symbols. Now I have a gallery of symbols. I want to compare whether that with this one, this matrix compares with which matrix in my gallery. So that's the problem. It's just that I know this matrix, so I know the size also. So those sizes also it will be sorted. So you can just compare. But what complicates the matter a little bit is that ideally this or like this, but then it might be slightly tilted. In which case the matrix will be completely different, and even gallery may not have. So you have to do that. But the beauty of it was when I gave this in this simplicity, the engineering college students were able to write the complete code. And usually in English, what they do is they take this matrix and they extract some they do some feature extraction, various kinds. And in some sense, what they are doing is you are giving them some material to see what it is. And like in any chemical lab, you put acid or stir it, grind it and all that, and try to analyze the salt. So what we did was we looked at the geometry of the objects. So we sorted without destroying the features. When you say you take the feature, you just say which are the ones here, which are the zeros, and evaluate some actually formulas, Zernike moments and all that. But by them you are actually destroying the complete picture of it. When the moments are same, you are saying they are probably same. But we looked at the geometry and we have more success. And I think we have some implications on the English OCR. So we can look at the geometry and classify. So finally you will only be there will be 2 or 3 to distinguish from, which can be done by other methods like language modeling. And there are problems that exist. There are very beautiful technical challenges. And what I am sad about is that the engineering and the science are not meeting properly to solve these problems. OCR is I am very happy about, and some of you may be familiar with it. This is something which you type OCR for Indian languages, you will see lots of results and papers on it, lots of claims also, but none of them are actually workable. So whereas our see for a Tamil thing, there is a magazine of the Ramakrishna Mission, Chennai. It's a 46,000 archive which have been scanned and which has been OCR, so that you can look through the scanned data using this OCR search. So it's a practical.
So, what's the number compared to A.G. Ramakrishna's?
Now this is where I want to. Is the A.G. Ramakrishna and things like that, I don't think they have actually done. For example, for a 50,000 page corpus, they have no results. So there is no comparison to that. The whole problem is that's what. So for people who may not know, there is this cell called the Technology Development of Indian Languages, which has been existing for nearly 20 years now. And I would say the output is 0. Yeah, unless you have a OCR or a good typing system, we can't send SMS on our mobiles. And the problem is the fonts. And the fonts, as I showed, is Bezier curves and curve fitting. Unless you have a mathematical description of the Kannada alphabet or Tamil alphabet, you will not be able to generate good fonts. And the OCR is the real surprising thing, because it's some 15-20 years, lots of IITs and IISc all get together and have not been able to come up with any OCR. Whereas the problem, if you look at it from scratch as we did, and comparison of matrices, was able to do it, and there is a practical thing. I mean, example there in the internet. I have done it for Kannada, and even the Tamil I have it on my laptop. So once I talked to not exactly AJR student, but PS Shastri student. They have a paper in Sadhana which they say is. And I told him, okay, I was struggling with it, and I said, okay, give me the segmentation algorithm. Recognition I will do myself. Then he said, oh sir, actually segmentation is done by IIT Delhi. So this whole simple problem was split into several components. Somebody does segmentation, somebody else does recognition, somebody else does pattern classification. But ultimately nothing has come out of that. So that was the thing. So there are real engineering problems which of course are not as complex as what he was suggesting, but which have a very deep bearing on our day-to-day life. For example, the reason that we have not been able to develop it means that the mobile phone is used only as a phone in Indian context. You can't send SMSs and no other power of the phone can be used. So if this happens, we may soon have a situation where the languages might survive in the spoken form, but in the written form we might all have to use the English language, because that has happened to the Turkish language. Turkish language replaced its original script sometimes in 1920s or so. They had a Turkish script, but they replaced it and they said we will use the Latin, the usual Roman script for this. So we might have such a situation. So that is the point. So the technology, if it does not help the local this thing, then you have a great danger of actually losing the language and the rich inherited culture, which is a sad thing, because language, English language, the current is after the Norman conquest, only 11th century. Whereas if you look at Kannada or Tamil, by 11th century we had such a huge corpus of material. All the we tend to get lost. So there needs to be, at more mundane levels also between engineering and mathematics, there are lots of things. So this matrix identification is itself a very beautiful, interesting problem. Just twist it a little, disturb it a little and identify which they are. So we do. Yeah, so if the samples are there and I can show you. And another small problem, it's a small problem, it's a big problem where we have looked at it from a very simple. So this is the error correcting codes. So error correcting codes are very important, we know that. And according to me, there are two very highly evolved, developed, fully tested error correcting code systems in the world. One is man-made, another is God-made. The God-made one is the human gene. Tamarind seed, if you put it, you get back the tamarind tree without much errors. And the man-made one is the Veda, Rig Veda. Rig Veda is by most of the standards more than 3000 years old. And the written version of the Vedas is less than 250 years old. The Vedas have not been written down, only of Max Miller and others. They have been handed over from, and then in what form? In almost pure form. So in what way then the system of recitation or chanting is the one, and that according to me is a error correcting code. What is called the Ganapata, with a lot of redundancy. It's like a block code. So what I was trying to do was, how do you talk about channel capacity in this? See, when you do these things, binary, it's easy. You have a string of zeros and one. The only way mistakes can happen is the 0 can be read as 1 or 1 can be read as 0. So you can do some probability consideration. But in the way they speak a word, then in what ways can you make a mistake? Because that's what the chanting will prevent. So it may builds the redundancy. You will repeat the same word. For example, if you have one line of Samhita Pata, straight recitation, the Ganapata is noted some 9 times or so. Each word is repeated 6 times. There is a very definite distinct for the end of sentence and things like that. So the error capacity, etc. Because now if you say, I have this letter, and in what ways can it be mispronounced or mistransmitted? So there is a very neat error correcting code tested over 3000 years. And is there some way we can actually come up with some numbers as to its? Ganapata must have been the ultimate thing, because that is the only thing. They did not think of a more complicated system. There are many systems, and this is the most complex form of chanting. So that's another topic in which I am interested. This information transmission, and in the human information transmission, the error analysis. Yeah.